Here we have a sled with a rider. It has a mass. And it's given an initial velocity. Velocity initial. We know both of those. We're given a fairly daring hill, actually. In my question, it's 11 meters high, and then it says cliff here. An 11-meter cliff is very radical. So this is, I'm not sure, I used to like a comic strip called Calvin and Hobbes, and he was traveling, he was often on a sled. So this sled is going to zoom along, and then the question asks, how far does it land? Way out here. You know, what kind of range does it have? Maybe I could put an R out here, range. How far away does it land? Well, we know that it starts out quickly, and by using energy thinking, we can imagine that it's going to slow down as it goes up here, as its energy is transformed from lots of kinetic energy, especially if we put down a coordinate system that says that as we go up in y, we start from 0 and go up to this height, we'll call this y max. As we go rise from 0 to y max, our kinetic energy is going to drop. Our potential energy is going to increase. And then after so we're going to end up with, on our sled, it's going to have a final velocity here. This final velocity horizontally is going to be less than its initial velocity. We know we're going to lose speed because we're going to lose kinetic energy because we're going to gain a whole bunch. Now when we're off, we ask how far. This is basically a projectile motion problem. How far is a function of how fast we're going and how much time it takes to fall. That's classic kinematics. So let's use this framework here. So we can tell that with this way of thinking, we can tell that here initially we have, well, conservation of energy can take us from down here to up here. Change in energy is equal to 0. The energy is the same down here as it is up here. What is the energy down here? There's a lot of kinetic energy, 1/2 mv squared, and there's no gravitational energy. If we call this level 0, the gravitational energy will be 0. Up here, the kinetic energy is, I'm going to call this initial velocity squared. We know that. We know that value. We're given it, so we can calculate how much energy is down here. The kinetic energy up here is going to be a combination. There's still going to be, the total energy up here is going to be a combination of the kinetic energy. There's still some left. It's going to be less. And a whole bunch is gained by mg, however high we are, y max. So, because we know y max, we know m, we know the initial velocity, the total energy up here is going to be equal to the total energy down here. The change in them is going to be 0. We can figure out what the speed is, or this velocity is, this horizontal velocity is. We can figure that out. We can solve. So now we know how fast the sled launches off the cliff. How far does it go? Well, in projectile motion has two major characteristics. One is you accelerate downwards with the speed of gravity, and the other is you have a constant horizontal velocity. Because there's no accelerations horizontally, because there's no forces horizontally, so we know that how far are you going to get? You're going to move through I'm going to put x final here. X final, if we call the base of the cliff 0, we can say that x final equals x initial plus velocity through time. This is the kinematic equation for uniform motion. There's no accelerations in here. We can call this 0. X final is what we want to know. This velocity is our velocity final that we calculated at the top. We can substitute that in here. What we do need to know is time, though. How much time does the sled have to make it this distance? That's still a question. Time is found by looking at the vertical motion. That's basically how long does it take to fall from here down to here. How long does it take to fall? Well, we can use now a kinematic equation in the vertical direction. To find that, that's x final is equal to x initial plus velocity initial delta t plus 1/2 a delta t squared. I chose this one because we know final and initial positions. Initial velocity in the y direction is 0. You don't start out up or down at all. Your initial velocity is only horizontal. And so if we convert this to the vertical direction, x final we could say is our y final, which is 0. Our x initial is, in the vertical sense, we started out at y max. There's no initial velocity in the vertical direction. 1/2, our acceleration is g downwards, so negative g, and we can figure out delta t from there. So, question is how far? To answer the question how far you end up, you have to know how fast you're going at the top. We figured that out using energy. Energy differences between down here and up here gave us a, actually there's no changes in energy, but at least there's a kinetic energy change and a gravitational potential energy change. If we track those changes, we can figure out what the velocity is, how fast he's going off the edge. And if we figure out how long it takes to accelerate from basically a stationary vertical velocity up here and fall to the ground, using this kinematic equation in the vertical direction, we can figure out the time. Combine those together and you can figure out how far the sled is going to launch.